And the next talk will be given by Adam McMaster, who will speak about first microlensing results from the SuperWASP Black Hole Hunter Citizen Science Project.
Thank you. Good afternoon. So my name is Adam McMaster. I'm a PhD student at the Open University in the UK. I'm going to tell you about the project that I'm working on for my thesis, where we are searching for black holes using gravitational microlensing in the archive data of the SuperWASP exoplanet survey. Before I get into that, it's not just me working on this project, so I thought I'd give credit to the people I'm working with. Almost everyone here is at the Open University, with the exception of Matthew Middleton, who is at the University of Southampton. Andrew Norton and Hugh Dickinson are my supervisors, and Stephen Sargent and Heidi Tiemann are colleagues of mine at the OU. Heidi was a PhD student. She's actually finished her PhD now and moved on to other things. So why are we searching for black holes? Well, the short answer is that there should be a lot of undiscovered black holes in the Milky Way. Since stellar mass black holes are the end stage in the evolution of massive stars, they should number, based on the number of large stars in the Milky Way and how old the galaxy is, there should be tens of millions of these black holes out there. But we only know of about 70 black holes, stellar mass black holes in total, almost all of which were discovered due to X-ray observations. So these are black holes that happen to be accreting matter from a companion and are very hot and therefore very bright in X-rays. There's only a handful of what are called quiescent black holes. That's black holes that aren't accreting matter and are otherwise completely invisible. There's only, I think, literally 3 of those that are known, maybe a few more. And I think they're all discovered in the last couple of years. So that's a huge gap in our knowledge of stellar evolution. And so we are trying to fill some of that gap. And we're specifically looking for quiescent black holes, which are in binary systems. So these are black holes which are orbiting with a stellar companion and lensing that's the companion. I'll talk a bit more about that just now. So everyone here probably knows a bit about gravitational lensing. So gravitational lensing is an effect that is most famously known in large-scale objects. So here I'm showing this is a large elliptical galaxy in the center, and the gravity from that galaxy is strong enough that it's creating a lensed image of a background, what's probably a spiral galaxy around it. So this ring around the elliptical galaxy is actually a much more distant galaxy, which is being brought into focus by the elliptical galaxy in the center. So here, that's a very large object acting like a lens through its gravitational effects. Now, on smaller scales, individual objects can do the same thing. So it's not just galaxies and clusters of galaxies that can cause gravitational lensing. Individual black holes, stars, neutron stars, and even planets can cause gravitational lensing on small scales, and that's called microlensing. We generally don't see an image of that. We just see it through photometry. So you'd see a magnification of a star. Now, normally, microlensing is seen for stars which are at much larger distances than the object that is lensing them. So it would be, say, a black hole, which is quite close to us, lensing a star that happens to be in the galactic center, for example. So they're not, the 2 objects aren't related to each other in any way. They just happen to line up. But we are looking for black holes that are in orbit with the objects that they're lensing. So those systems would look something like this. So we know from simulations that have been run previously that we would expect to see say you had a star that was sort of 1 to 10 solar masses, we'd expect to be able to see black holes, a black hole orbiting that at a distance of between 10 and 1,000 AU. That's quite a big range of distances. And at the upper end, that's actually quite a huge distance for a black hole in a binary system. There aren't any that have been discovered at those sort of distances yet. And we'd expect to see black holes of a mass between 2 and 50 solar masses. And that equates to an orbital period of between 50 and 5,000 years. So we're not really expecting to see any repeating events in there. We'd have to get pretty lucky to be able to see more than one microlensing event in our lifetimes. But we're hoping to be able to find at least a few one-off events. So as I said, we're using archive data from the SuperWASP survey. I imagine many people here already know what SuperWASP is, but for anyone who doesn't know, SuperWASP was a ground-based search for exoplanets using the transit method. The SuperWASP project consisted of 2 telescopes that looked like this, each of which had eight individual cameras on one big moving mount that could pan across the night sky. And between them, so there were two locations, one in the Canary Islands and one in South Africa. And between them, they observed almost the entire night sky, excluding the galactic plane, which is the stellar density is too dense for the cameras to resolve the individual stars. But it observed more or less the rest of the night sky for about 12 years. And in that time, it discovered almost 200 exoplanets, which, unless I'm mistaken, I believe that makes it the most successful ground-based exoplanet search to date. It's outnumbered only by the space-based searches. So in the course of the decade or so that it ran, SuperWASP observed 31 million different sources and produced a photometric light curve for each one. That's a huge amount of data, which contains a huge amount of information about the stars that were being observed. So we're now looking through all that data, trying to find new things and trying to make the most of the data that's already been collected. But that data is quite noisy. The SuperWASP survey was designed specifically for exoplanets, and it was very good at finding those. But the data is affected by things that weren't a problem for the exoplanet search, but are a problem if we're looking for things like stellar variability and microlensing. There's a lot of noise in there that makes it hard to do an automated search. So because of that, we're using citizen science to search to carry out our searches. So we're getting volunteers, members of the public, to look at the data and look for the various things that we're finding. So the Black Hole Project is actually the second citizen science project that we've run. The first was called SuperWASP Variable Stars. That is actually still running. That's been running for a number of years, and it's been quite successful. It's looking for a handful of different types of periodic variable stars, and it's found a number of new variable stars that were not previously known, as well as taken updated measurements of previously known variable stars. So that is still ongoing. I don't have time to say much about it today, but people may be interested in checking that out if you haven't already seen it. So the Black Hole Hunters project, it looks like this. Both of these projects, I should say, are run on the Zooniverse citizen science platform. The Zooniverse, if you're not familiar with it, is a platform that allows researchers to build interactive citizen science projects that the public can log on to online. So what we do is we show the volunteers a light curve that looks like this. And I should say on the bottom right here, I've overlaid a diagram showing how the geometry of the lensing corresponds to the peak in the light curve. So you can see the top of the peak corresponds to when the black hole is in the center of its transit across the star. So we show a binned light curve with 2 different types of binning on it. So there are red circles and there are white squares. The red circles are a nightly bin, so there's 1 red circle per night, and then the white squares are a handful of bins per night. And the idea there was to give a simplified way for members of the public to judge how noisy each night's data was. So we could have put error bars on there, but we didn't want to have to explain to people who weren't familiar with them what error bars are. So we thought we'd make it a bit simpler, and this way you can sort of judge by eye how much scatter there is, because you can see the points, but it's not as overwhelming as showing the unbinned data, which is quite messy. So the volunteers are given quite a simple instruction. They're told to look for any symmetrical peaks that last for at least 4 nights, and then we just ask them a yes or no question: can you see a sharp peak in the graph that might indicate a hidden black hole, yes or no? So that project launched at the end of October 2021, and it finished about a year later. And we've currently paused the project while we analyze the results from that first batch of data. So in that year, well over 5,500 volunteers submitted 2.1 million classifications between them. So each light curve is shown to more than one person, and then we put their results together and come up with a consensus answer for each light curve. So those 2.1 million classifications were for about 200,000 or so different light curves. I'd say a subject in the Zooniverse terminology, a subject is an individual piece of data that you show to the volunteers. So I'm currently writing up the results from this, and I'm following sort of this process. So we've taken all of the votes from the public, and we put them together and come up with a list of all the light curves that the volunteers think have anything that could be a microlensing event in them. I've then manually gone through all of those to remove the false positives. We're actually expecting a lot of false positives, just because we expect real events to be quite rare, and there are lots of things that can look like a microlensing event but aren't. And I'm currently at the stage of fitting computer models to what was left after I removed all the false positives. And I'll show you some of the results from that in a moment. And then once I've got the final set of results from the computer modeling, I've got some ideas for how to follow up on some of these objects and figure out if some of them might actually be black holes or not. So just from the photometry alone, we can't be certain that any of the events we're looking at are actually black hole microlensing events. Because like I said, there are other things that can cause that as well, that can cause the same effect as well. So I've got some ideas for how we can try and get some further evidence to support some of these, but I'll talk about that at the end. So here are the numbers of results that we had. We had over 1,000 initial candidates from the Zooniverse. That's huge. That's more than we expected to get. And after going through those, there are about 70 left that to me look plausible and that I couldn't explain any other way. So there are some other effects. For example, most of the false positives we got were due to the full moon. We heard in talk a minute ago how the full moon can cause a spurious increase in brightness. We actually didn't expect that to be so prominent in the objects that we found, but we found more instances of the full moon than anything else. The moon sort of became our nemesis while we were looking through these. So let's have a look at some of the results. This is an overview of the results, and I should warn you, these numbers are very early. I haven't finished the analysis yet, and these might very well change before this is published. And also just a reminder that we can't actually confirm that any of these are black holes at this stage. These are still candidates, not confirmed black hole discoveries. One other caveat is that, so on the top left here is the distribution of masses of the candidates. Those numbers are very rough. We can't actually definitively say what the masses of any of these objects are from the data we've got, because the effect of the black hole's mass is actually quite small compared to the effect of how far apart the black hole and the star are. So that effect is small enough that we can't quite measure it with the data that we have. But we know from simulations what the likely masses are and what the distribution should look like. So we've kind of taken our best guess and weighted them against our expectations, and that's sort of the distribution that comes out. Then up here on the top right is the range of orbital periods. Most of them are in so this is in years. Most of these are in the hundreds of years, and then there's a few that are up in the thousands. I think there's one that's 6,000 or 7,000 years. So like I said, those are pretty big numbers for a black hole in a binary system. Usually the orbital period would be measured in days. So if these turn out to be real, that would be a whole new area of the sort of black hole population that we're looking at. And on the bottom here are the orbital separation between the star and the black hole at the point that we observed it in astronomical units. And on the bottom right is what's called the impact parameter. So that's how lined up the black hole and the star are. So a value of 0 would mean that the black hole went right across the middle of the star from our point of view. And you can see that most of them are about 2.5 to 3. That means that so if you imagine they're sort of lined up like this, 3 would be, the black hole would be up here somewhere. And that's just how the geometry happens to work out with the way that the lensing works. So I've picked out 4 of my favorite candidates so far. These are sort of 4 of the best looking ones. This is what the data looks like. There's a lot going on here. Don't worry too much about all the detail. On the top right, you might recognize the original light curve that the Zooniverse volunteers were shown. What I've done for my analysis is I've taken, so in this case, this is the peak that the Zooniverse volunteers were talking about. So I've recentered that and put it in the middle and put sort of 30 days either side of it. And then there's a few different colors of points on the plots that I'm using. The light blue ones are the original SuperWASP data. So you can see that you can see nicely each night's observations is kind of in a column because there's a gap during the daytime. But you can see there's quite a big range of flux measurements each night. I've put those together into a sort of weighted mean average value, and those are shown in orange with some error bars. And then in green is the sort of best fit computer model of what the black hole would have to be like to produce that light curve. Then on the bottom here, these are the results of the computer simulations. Again, you don't need to worry too much about all the detail, but what we're hoping to see here are, so these are the various parameters that we're fitting in our models. And what we're hoping to see is that these converge nicely to some well-constrained points. And on the right is roughly the same thing. This is a comparison between different values. And what we're hoping to see here are these nice, neat circles showing that the fitted values are nicely constrained. So in this, okay, thank you. So in this case, if this is a real lensing event and that model is the best fit, then the orbital period would be 95 years. Now, this one is a bit less clean. You see there's this peak here. I think that is due to the full moon, and you can see there's error bars. The error bars are quite big there. This one's interesting because it's got actually 2 different peaks in a lot of the values. So it's sort of a bimodal distribution for the values. So in this case, I don't think the best fit, the closest fit, is necessarily the most realistic one. Because the black hole mass that corresponds to is quite high. It's 23 solar masses, so that's probably not very realistic. A lower mass would be more likely, and would probably correspond to some of the sort of higher values for the distances and so on. So so there's some more work to do there to try and get a more realistic fit out of that one. And this is quite a nice one. This one shows how the volunteers are quite good at spotting quite small increases in magnitude. So that looks like quite a convincing increase in magnitude to me, because you see the lower values sort of disappear, and it's the average is up there. But that would be quite hard to find automatically because it's kind of within the scatter of the sort of background noise. So that's a great example of how good the volunteers are at finding the things that would be impossible to find just with software. And the last example there, I just like this one because it's got quite a nice clean shape. And again, I think all of these have quite long orbital periods. Well, they're on the shorter end of the distribution, but they're all, so that's 95 years, 125 years, 473 years, and 202 years. So far, I haven't found any that we would actually be able to observe another lensing event, which is a shame, because if we happen to have one that was maybe 20 or 30 years, then I could look forward to being able to maybe confirm it directly by observing the next one, but we haven't managed to find any that short, unfortunately. So that's where I've got to at the moment. I've got some ideas for ways that I can follow up on these to try and get some more evidence to support them. I don't have time to go through all of that now, but if there's anything that you're interested in, you can ask me in the questions or afterwards. And just a little summary of what I'm going to do next. I'm going to finish the fitting and analysis of this data, try and follow up on any of the promising ones, and hoping to write a paper which will be out later this year. Then we're planning for a follow-up project using data from TESS, and also maybe one with ZTF if we can get the funding to do that. So that's what's coming up next. Thank you.
Thank you. Questions?
Thank you. Actually, I have two questions. One was almost answered on the previous slide about the follow-up observations. Maybe you can tell us a little bit more. There is a pity the next event is far in the future. So I was wondering what kind of follow-up observations you can do. And second question, can you compare or tell us what is the advantage to use the volunteers in comparison with some machine learning method?
Yeah, I'll answer the second one first. So at the moment, we don't really have a method to find these sorts of events in this data because it's so noisy. To do machine learning, that is something we'd be interested in, but in order to do that, you need a large set of labeled examples to train the machine on, and that's one of the things that we can do with the Zooniverse. We can get people to label all of the examples and then maybe train a machine learning model later on. So that is something that's sort of in the back of our minds that we're going to try and look into. In terms of following up, basically my strategy for following up on these is to look at every other survey that's published data and see if there's any more data on any of these. The ideal would be to find multi-band observations of some of these, because microlensing events should be achromatic, so you'd see the same magnification in every filter, whereas other things that would cause the same effects would vary in different colors. So that would be the best way of confirming some of these. But yeah, there's lots of data out there. So basically, I'm going to see what data is available for these candidates and then see what I can do with it.
Other question here?
I have a question about the periods of the objects. I see, because of nature of your data, you can see mainly the longer transits, focusing events. So there is possibility that in other types of data there will be closer pairs or closer objects to a star, and that will be pretty close. If it will be like I don't know, event of order of hours, will be there also an interaction with the star in such case? So if this approach also it may be also used for closer pairs than you are presenting.
I'm not sure what the lower limit would be for the orbital period. If, as you said, if it's close enough, then it will start accreting matter from the start, and then it becomes obvious in X-rays, and it would be much easier to find it that way. Yeah, I'm not sure how short we could go with the orbital periods. Obviously, we're limited by the observations as well. Maybe with something like TESS or something, we could maybe find shorter ones. But yeah, at this stage, I don't know how short.
This is really interesting research you presented, but I'm interested to understand which method have you used to rule out that the observed microlensing light curve is not caused by any other object. So what makes you sure that this is a black hole as a possible explanation instead of maybe, I don't know, a main sequence star or something else causing the microlens?
So a lot of the sort of limits we've set on, so that like the 4-day limit and all those sorts of things are based on simulations that were run by someone else whose name I've forgotten. So there are simulations of what we expect these sort of self-lensing systems to look like, and that does depend on sort of the evolution of the systems and so on. So if it was a star, then I think it would fall outside of the parameters that we've set. And also, you'd be able to resolve a stellar companion as well. One of the things that I might do to follow up is try and get like good deep imaging of each of these systems and just confirm there isn't anything visible there that could also explain it.
I would recommend to look at the black hole Tom. I mean, I mentioned it during my presentation, the Gaia alerts. They have a website which have from the Gaia alerts candidates of microlensing events, and I have followed a couple of them. And the black hole Tom is the database where you can see the different kind of systems, and the data actually is also there, which showed the microlens and so on.
Yeah, I noticed that when you said it. That does sound interesting. We're interested in doing in maybe looking at Gaia and looking at also we're looking forward to Rubin as well when that comes online. So we're always looking for more, wider casting a wider net and then seeing what else we can do. So yeah, I made note of that when you mentioned it.
No more questions? Okay, so thank you very much again.